Hello, this is Mr. Craig, and this is day 19 lecture video for stoichiometry precipitation reactions. So we get to utilize what we've learned by memorizing the solubility rules, and I'm glad that you guys have memorized the solubility rules because that's what you're supposed to do. So let's go ahead and get started. So we are going a little bit above what the last lecture dealt with just memorizing the solubility rules, but now we're going to implement them into our stoichiometry. So based on what we did in stoichiometry before, we were predicting the product. We're still predicting the product. However, now we're doing this for precipitation reactions. These are just double replacement reactions where you have a precipitate. And I'm going to give you a heads up. If you ever see a question like this on a test or an AP exam, I guarantee you there's going to be a reaction. There would not be a no reaction on a situation like this where they're giving you data. They've given, like in this question here, it's giving you a volume and a molarity for two different things. So we have a limiting reactant reaction, we have a precipitate reaction, we have a solubility rules that we have to know, and writing no reaction, the question's been wasted. So every one of these reactions will take place. So don't write no reaction and say, hey, it's not going to produce anything. I will never do that to you. The AP exam would never do that to you. So, and again, like what we talked about when we were learning the solubility rules in the last lecture, there are certain things that just stand out, like group 1A, the chlorates, the nitrates, the acetates. Those things are glaring, or they should be at least for you after a while. I'm not saying necessarily the second day that you've been exposed to solubility rules that those are going to jump out at you. However, there should be some things that you start to recognize as we go on throughout the year. All right, well, let's get started here. Question number 1 says, calculate the mass of a precipitate that is produced when 70.5 milliliters of a 5.2 molar solution of sodium phosphate is added to 137.3 milliliters of a 3.5 molar lead 2 chlorate solution. So again, we know we have a stoichiometry problem because we have more than we have more than one reactant. So we have something going on in a reaction. Also, we know we have a limiting reactant reaction because we are given two amounts of the stuff that we start with. So, hey, these are the best kind of problems. These are the real life chemistry situation type of questions that you'll be exposed to if you become a chemist later on in life. All right, so let's go ahead and get started. Step 1. What is step 1 in stoichiometry? Write a balanced equation. So let's go ahead and write a balanced equation. So the question's actually right here. It says calculate the mass of the precipitate. Okay, so that's what we're looking for. All right, so we have 70.5 milliliters of a 5.25 sodium phosphate. And let me go ahead and write sodium and then phosphate. We'll balance the formula here in a second. Is added to 137.3 milliliters of a 3.5 molar lead 2 chlorate. What does the Roman numeral 2 there mean? That's right, it means a +2 charge. Doesn't mean there's two leads. It means that each lead has a +2 charge. Now, there may be two leads based on what the nonmetal's charge is, but it's not too likely. All right, so lead 2 chlorate, and again, chlorate is ClO3. Okay, and we'll come back and we'll bounce those here in a second. And then it forms, and again, since this is a double replacement reaction, I'm going to go ahead and put the sodium with the chlorate. So Na, ClO3, and we'll bounce that here in a second. And lead with the phosphate. Now, always write the metal first. Lead and phosphate. Okay. All right, so now let's go. Now that we've got all of that, let's go ahead and bounce charges. So sodium has a +1 charge, phosphate -3. So that means we need 3 sodiums. Okay. Lead we know is a +2 based on the equation right there. Excuse me. Chlorate is a -1. That means I have more than one poly, so I need 2 of those. +1, -1. Hey, that one's bounced as written. And then we have our lead stays the same charge, even though it could have multiple charges. It could be a 2 or a 4. You don't need to know that. Phosphate is always a -3 charge, so that means we have a -3 and a +2. So that means I need 2 of these and 3 leads. All right, so that's our first thing. We've got our formulas balanced charge-wise. Now let's balance the number of atoms on both sides. Go ugly early is what I say. So this one is my ugly one, the lead phosphate. So since the lead phosphate is my ugly one, I'm going to erase some of the things on here. I'm going to erase the charges. Let's kind of clean this up a little bit here. Get that? Okay, thanks for being so agreeing. Man, nobody wants to be erased here. Okay. Alrighty, got the charges, those miscellaneous underlines. Alright. Okay. So I'm going to go ugly early, so it doesn't matter if you want to start with the lead or the phosphate. I've got 3 leads, so let's get 3 leads. Okay. So now I have 3 leads, that means I have 6 chlorates. So put a 6 there. I have 6 chlorates, 6 sodiums. So to get that, I'm going to put a 2 there. Switch you over just for a second. Okay. So now I've got 6 sodium, 2 phosphates, 2 phosphates. Hey, this is balanced. Great. All right. Now, so we have the number of atoms balanced on each side. We have our charges correct. Everything's golden. Now, let's go ahead, before we write down the other information, let's find out who the precipitate is. Okay, again, we don't really care about the reactants. Sometimes I will give you a solid that's not soluble on the reactant side, but it'll dissolve when it reacts with the other things. So don't worry about the reactant side. Only worry about the product side. So we only care about the precipitate on the right side of the equation. So that's what we want to focus on. So go ahead and erase that. So let's see here. Sodium and chlorate. Is this your precipitate? Well, hopefully you're saying no because of 2 reasons. First one is sodium is a group 1A metal. So anytime you have a group 1A metal, all of those are soluble. The second reason is chlorate. Well, that's the same category as acetate and nitrate. So no, we will not have our precipitate on the sodium chlorate. Lead phosphate. Remember with phosphates, all phosphates are not soluble except with group 1A and ammonium. Well, we have lead, so that means that this is our precipitate. So do circle and write PPT. Okay, so now we can calculate the mass of the precipitate. So the question's asking, question mark, mass, which will always be in grams. Okay, and again, remember, moles is not mass, grams is mass. So we're actually looking for the mass of the lead phosphate. Okay, so we've got pretty much what the question is asking, so now let's find out what we know. So we have to write down what we know. We have 70.5 milliliters of a 5.2 molar solution. So I've got a volume, 70.5 milliliters of a 5.2 molar. And if you wanted to do this before you balance the equation, that's probably a good idea. Nothing wrong with that. 137 milliliters, I'm sorry, 137.3 milliliters of a 3.5 molar solution. Okay. So now we've got essentially step 1 completed at this point. So we have everything. All right. Since we have 2 reactant amounts, we have to find out which one we are going to use to answer the question. We're not going to find out how much each of these makes. That's not what we're doing. We're finding our limit. We're going to do our limiting reactant step. Okay, so your limiting reactant step, pick one of the reactants. It does not matter. Pick one. Okay, I'm just going to pick the sodium phosphate since it's listed first. So again, what we're going to do is we're going to compare the sodium phosphate, how much lead chlorate will be needed to completely react with all the sodium phosphate. So again, if we know our volume and our molarity, we always start with the volume, because what is step 2? Change what's given into moles. So when we take the volume times the molarity again being moles per liter, we're going to get rid of the volume by multiplying the volume times the molarity. So we'll be left with moles, which is step 2. So let's do that. So start off with your 70.5 milliliters. Okay. Well, since molarity is in moles per liter, okay, we need to convert the milliliters to liters. So we're going to go liter, and in 1 liter, there's 1,000 milliliters. Okay. Then remember that molarity is moles per liter, so we have a 5.2 molar solution, so 5.2 moles for every liter of the sodium phosphate. Okay, so this is all step 2. So we've changed our volume into moles. I've multiplied the volume times the molarity to get the moles. Step 3, we need to use the mole ratio, so we're going to get rid of the moles of sodium phosphate and convert this to moles of lead chlorate. Again, that's the whole point of the mole ratio step, to get rid of these units to get these units. Okay, so we need to be able to change the values here. All right, the whole reason why we balance the equation is so that we can get the values for step 3. So we have our coefficient of 3 for our lead chlorate, and then the sodium phosphate has a coefficient of 2. So this is step 3. Okay. Alrighty. Step 4 says, ooh, I didn't want to do that. Sorry, guys. Step 4 is we want to convert to the desired units. So what that means is we need to go back to the units that was given in the problem. So we're going to go back to volume. We're not going to go to molarity. We're going to go back to volume because we have 137.3 mils. So I want to get rid of the unit moles of lead chlorate. And how in the world could I ever do that? Well, I'm going to take my molarity and I'm going to flip it. Okay, so my moles are on the bottom. That means I have 3.5 moles on the bottom. Again, molarity is moles per liter, but this is also saying that if I have this flipped, that means I have this many moles for every liter of solution. Okay. Oops. Erase, please. Thank you. All right. So, and that is for every liter. Then I convert the liters back into milliliters. And again, there's 1,000 of those. All right. So now I want to get a value here. And then we'll talk this through. And I'll ask you who the limiting reactant is. So 70.5. Now I'm doing this on my calculator here. I don't want to try to type this in on the computer. Okay, and then use your parentheses on the bottom. So we have 2,000 times 3.5. So 157 is what I got for my answer here. And I'll double type that again just to check and make sure. 70.5 times 5.2. 3 divided by 2 times 3.5. Yep, I like that. All right, so what this is saying, okay, and this is my lead chlorate. Lead 2 chlorate, sorry. Okay, all right, if I were to use all 70.5 milliliters of my sodium phosphate, okay, use all of this, I would need at least 157 milliliters of the lead chlorate. Okay, I would need at least 157 milliliters of the lead chlorate. I do not have 157 milliliters of the lead chlorate. So that means that the sodium phosphate will not be completely reacted. Therefore, my limiting reactant is my lead chlorate. Okay, that's my limiting reactant. Now that I know who my limiting reactant is, I can answer the question. Looks like I need to space this a little better here. Sorry guys, let me give me a second here. All right, I'm going to scoop this down. Okay, we'll come back here. All right, looks like I need to write it a little smaller, but that's okay. I apologize if it looks sloppy. This screen is not the best. All right, so what this means is that I'm not even going to look. Whoa, what happened there? Let's go back to undo. That's pretty cool. That looks neat. Review. Okay. All right, so I'm not even going to need this value here. I'm only going to use this information here since that's my limiting reactant. All right, so now I can answer the question for what mass of the precipitate is going to form. So what do? Same thing as I did before. I'm going to start with my volume and molarity, so I have 137.3 milliliters. 137.3 milliliters of lead chlorate. So 3. Okay. And I need to, actually I probably need to erase that. Let's quench this up a little bit better here. That's my lead chlorate. So convert that to liters. I'm sorry, milliliters. Poor pen is not having a good day today. It is humid today, so that might be one of the reasons. All right. My molarity for that is 3.5. And that is moles per liter. Don't ever write big M within the problem. And that is my lead chlorate. Okay. My mole ratio, I'm going to get rid of my lead chlorate. And I'm going to go to lead phosphate. And that's a 2, and that's a 3. And then my values, I've got a 1 for my lead phosphate and a 3 for my lead chlorate. So a 3 and a 1. Okay. Now, the question wants to know what mass. So, how do I do that? Well, if it's not the unit I'm looking for, I move it diagonally. So I'm going to get rid of moles of lead chlorate. I'm sorry, phosphate. Okay, and I need to find the molar mass for that. So I need to go to my periodic table. I've got 3 leads. Lead is right here, 207. So 3 times 207.2, and I'm going to add that to my phosphate, which I have, what was it, 3 of them? 2 of them, sorry. So 2 phosphorus, which is, so add that to 2 times 30.97. And I'm going to add that to, I believe, 8 oxygen, 4 times 2. And my oxygen is 16 grams. So add that to 8 times 16. And the molar mass, that's a big one, is 811.54. Okay, I'm going to leave that in my calculator because I'm going to use that here real soon. 811.54, and that's grams per mole. So, my mass that's going to be produced, I'm going to leave that value in my calculator, multiply it times 3.5 times 137.3 divided by, use parentheses, 3,000. So that doesn't look right. Let me do that again. Times 3.5 times 811.54. So 129.99, we'll say 130. So 130 grams. Okay, and that is of the lead phosphate. Now, this may have taken a little while, and you're right. These types of problems do take a little bit longer than other chemistry questions. And again, these are the types of questions that you should expect in real chemistry situations. And yes, these are real-life applications. Okay, number 2. Let me scoot this guy down just a little bit further. Okay. Give myself enough room. Sorry about this. All right, go back. And again, at any time if you need to pause, take a break here, it's fine. That's why I love these videos. All right, number 2. Calculate the volume of a 5.65 molarity lead 2 nitrate solution that will produce a 45.7 gram precipitate. You get to determine the precipitate when reacted with calcium chloride, which is in excess. Now, my question to you is this a stoichiometry problem? The answer is yes. How do we know? Well, first of all, this is our homework, stoichiometry. Okay, so hopefully you recognize that. But also, more importantly, we have 2 reactant amounts. We have lead nitrate and we have calcium chloride. So we're reacting 2 things together. So that tells us, yes, we have a stoichiometry problem. However, do we have a limiting reactant problem? And the question is, yeah, kinda, except we know who the limiting reactant is because it says that the calcium chloride is in excess. So we don't need to do any calculations to determine who the limiting reactant is. But we do know who the limiting reactant is because the question essentially tells us who the limiting reactant is. All right, so step 1, it is stoichiometry. Write a balanced equation, so your volume for the lead nitrate, lead 2 nitrate. And again, we'll write these first, and I'll put the charge there since it told us that. And I'm going to go ahead and write what I know. 5.65, what is that, molar? Okay. And that's going to react with calcium chloride. And that's plus 2 minus 1. I'll just go ahead and do it now. Okay. And 45 grams of precipitate. So we get to figure out who need to determine who the products are. So lead chloride. And again, lead's going to keep its plus 2. Chlorine's going to keep its minus 1. So again, we're not carrying this subscript over. We need 2 of these because lead has a plus 2 charge. Okay, we never carry subscripts except on polyatomics. And then calcium nitrate. And calcium has a plus 2 charge, so that means we have 2 nitrates. All right, and it says so we need to determine who the precipitate is. So solubility rules. Lead, actually not lead, chlorine. Chlorine, bromine, iodine. Soluble with everything except silver and lead. And Hg2 plus 2. Okay, so you make sure that you know that one as well. Okay, so is this a precipitate? You better believe it is. There's our precipitate right there. Now, this is not a precipitate because we have our nitrate. Okay, so we have 45.7 grams of our precipitate. All right, now this is a little bit of a interesting type question, and I like this question a lot because the question wants to know what is or calculate the volume of a lead 2 nitrate solution, okay, that will be used to produce 45.7 grams of the precipitate, which in this case is lead chloride, if we have enough calcium chloride to do that. So this is in excess, so we don't need to worry about how much we have of this. Don't stress over it. However, the question is, what is your volume? Okay, and does it say that it needs to be in milliliters? It doesn't. So if you want to leave it in liters, that's fine. If you want to convert it to milliliters, that's fine. You don't have a problem with that. However, the nice thing is there is no limiting reactant step. All right, so if we're looking for this right here, then we should not ever want to start with the 5.65 molarity. That is correct. So we're going to start with this. Because again, step 2 is to change what's given in the moles. We don't have enough information to change this information in the moles. Besides, that's what the question's asking, so we can't. We can't even think about starting with that, okay? However, do we have enough information from the 45.7 grams to convert that into moles? Absolutely, so that's why we want to start with that. So, step 2, change what's given. And again, the is given is the complete information that will get you moles. And this is lead chloride. Okay. So one step here, lead chloride, and I want to say it's 207.2. We just looked at it a second ago. Yep, 207.2. Okay, so 207.2 plus 2 chlorines, which is 35.45. Double check that. Chlorine, 35.45. Good. Okay. So my molar mass for the lead chloride is 278. And that's 0.1 grams. And we do not want to round that. That is not our final answer, so do not round. So this is all step 2. Change what's given in the moles. Step 3, we want to use a mole ratio, so we're going to... Did we balance that up there? We did not balance that yet, did we? Actually, we did on accident. Sorry about that. We have 2 nitrates, and the only reason why that balances is because both the metals are +2 and both the non-metals are -1. So yeah, we accidentally balanced that, but we still have to double check, make sure that everything's correct. So lead chloride, that's a 1, and then 1 mole of what we're looking for, which is our lead nitrate. Now again, yes, we do need to show this step because it gets rid of the units that we start with and the units that we're looking for. All right, so if I'm looking for the volume here, again, my molarity is moles per liter, or how many, I have 1 liter, that means how many moles. So in this case here, if it's not the unit I'm looking for, dimensional analysis, I need to move it diagonally. So the best thing to do here is to move it diagonally. So I'm going to have my moles on the bottom. Let's actually get the pen up and running. So 5.65 moles for every liter. Now, if you want to go to milliliters, you'll go one more step. I'm just going to leave it at liters unless it says to go to milliliters, and volume just says volume. Okay. So I'm pretty much done with the calculation part. Just have to type it in. All right, so 45.7. Wow, that was easy. Divided by answer times 5.65. So it says 0.029. We'll say 291. Okay, and that is liters. If you wanted to change that to milliliters, multiply that by 1,000, and that'll give you 29.1 milliliters. Okay, so your call. You get to decide how you want to finish that problem off. But the nice thing is, this one wasn't as involved as the last one because we knew who the limiting reactant was. Therefore, you don't have to calculate who the limiting reactant is. All right, number 3. Number 3 is a fun one. It says a student dissolves 34.2 grams of sodium chloride in enough distilled water so that the final volume is 0.75 liters in a volumetric flask labeled A. Then in a different flask, she dissolves 63 grams of silver nitrate in enough dissolved water so that the final volume is 0.63 liters in a volumetric flask labeled B. Then she mixes the 2 solutions together. The question is, what is the mass in grams of the precipitate formed? Okay, so it looks like she made 2 solutions and then poured the 2 solutions together. Okay, so she in volume in a volumetric flask, which this is not a volumetric flask, she made a solution of sodium chloride. Wow, that's really good work there. Okay. Oh boy. Sorry. Okay, so sodium chloride, and then in the other container she made silver nitrate. Okay. Then what she did was she took A and B and poured them together. So by pouring these together, she made a solution and hopefully a nice little precipitate. Now these are soluble. We know that based on our solubility rules. Again, group 1A and chlorine, so soluble. The nitrate, anything with nitrate is soluble. So these things are soluble, but when these two mix together, I'll bet you there's a precipitate that's formed. So the question is, what is the mass in grams of the precipitate formed? All right, so here's the interesting thing, though. We are given a mass amount, and then we're given a volume. What do you think we're going to do with these volumes? Well, unless you want to do a lot of work, I would do nothing with these volumes. Can you convert these grams into moles? Absolutely. So really, these volumes are just distractors. Now, we could find out what the molarities of these things are and do a lot of fun stuff, but essentially what's going to happen is we're always going to resort back to our number of moles. Again, no matter how much water we add to this, the moles is not going to change. The molarity will change, but the moles will remain constant. All right, so let's write out our balanced equation first. So we've got, and the bad news is these are all plus ones and minus ones. So sodium chloride and silver nitrate reacts together to form sodium nitrate and silver chloride. Okay, and they all have plus one, minus one, so we're golden there. The sodium chloride has a mass of 34.2 grams. And again, the volume's given, but don't worry about it. The silver is 63 grams. Okay. And the question wants to know, what is the mass of the precipitate? Okay, well, let's find out. Who is our precipitate? Well, sodium nitrate, is that a good precipitate? No. The reason, again, we have a group 1A metal, never forms precipitates. Nitrate never forms precipitates. So silver chloride, all chlorine, bromine, and iodines are soluble except with silver and lead. So there's your precipitate. So there's our question. How many grams? Right there. Okay. Do we have a limiting reactant problem? You better believe we do. So let's find out who the limiting reactant is. Now, there's a neat way of doing this without going too crazy and having to pick the wrong limiting reactant. But we always want to show who the limiting reactant is because that's always worth points. Now think about this. Even though the gram amounts are different by almost half, or the other one's almost twice as much, think about the molar masses of these things. Sodium has a molar mass of about 23. Chlorine, about 35. Silver, about 110. And then we've got a lot of things. So this is a very massive compound. So even though we still have to determine who our limiting reactant is, it's probably not a bad idea to try to start your limiting reactant calculation with the limiting reactant. If you can deduct that, oh yeah, this thing's a lot more massive, I don't think it's, I think it's the limiting reactant based on an educated guess. Because sometimes these questions, and I want you to get into the habit, sometimes these questions will ask you, well, what's the amount of the excess? How much of that still remains when we get done with the question? So it's just a good habit to kind of eyeball it and say, you know, I think that's the limiting reactant. And then again, we always prove it or support it by doing the calculation. So let's do that. So we have 63 grams, and again, this is our limiting reactant step. You always want to show that because this is worth points. And typically it's a big chunk of points. Even on the AP exam, it's still worth a big chunk of points. So you always show it. So we've got 63 grams, 63 grams of silver nitrate. And we need to convert that to moles. Okay, so let's find out what the masses are. We've got one silver, which has a mass of 107.87. So 107.87 plus, was it nitrate? Yeah. So one nitrogen and three oxygens plus 14.01 plus 3 times 16. So around 169.88 is my molar mass, so 1 mole of silver nitrate. And again, might be totally off the mark, but again, I'm just throwing an educated guess out there. Let's see here. And then, so that's step 2. Step 3, let's get rid of that unit, moles of silver nitrate, and go to moles of sodium chloride. And then 1 mole of sodium chloride. It has a molar mass of sodium is 22.99 plus 35.45. Again, I'm getting these values from here. So 22.99 plus 35.45. And that gives me a mass of 58.44, which is about a third, a little less than a third of the molar mass here, and this is just a little bit. So I'm pretty good guess that the silver nitrate is the limiting reactant, but let's do the calculation. So I've got my 58.44 on top, times 63, then divide that by just 169.88. So that gives me a value of, what is that, 21.67. So we'll say 21.7 grams. All right, now what this is saying is that if I use all 63 grams of silver nitrate, I will only need 21.7 grams of sodium chloride. I have more than I need. So my limiting reactant is the silver nitrate. And again, hopefully, and again, I'm not expecting you to be able to look at them right now and deduct from that, but you will. By the time we roll around to May, you'll start looking at that and going, oh, that one's a lot more massive, and we've got double the amount or half the amount or whatever. So you can do some quick estimating, and that'll save you some time. So if the question was asking, okay, we know we're going to use all the silver nitrate, how much of the excess remains after the reaction's all done, then we're in great position. All we have to do then is take the 34.2 minus how much we used, and that would give us how much of the sodium chloride was still floating around or in solution. Okay, so but that's not what the question's asking. So let's get back to what the question's asking. It wants to know how much of the silver chloride is being produced. All right, so now that we know who the limiting reactant is, and we had a pretty good guess at the beginning, we're going to start with our limiting reactant amount. Again, it's silver nitrate. Yeah, silver nitrate. And we'll convert that to moles, so that should look very much the same. So we already did that math right there, which looks very nice. So that saves us some time. We don't have to recalculate that. So silver nitrate, and 169.88. 1 mole of silver nitrate goes on the bottom. 1 mole of silver chloride goes on top. Then it wants to know what is the mass, I hope. Yep. What is the number of grams? So we need to find out what the molar mass of that is. So let's check it out. Silver again is 107.87. Oop, I did the wrong number. 107.87 plus, is it nitrate? No, chloride, sorry. 35.45. See, the chlorine's right here. So that gives us a molar mass of 143. That's our molar mass, and that's not our final answer. 143.32. And let's do the calculation. So we have that value in our calculator. That one should still be in your calculator. Hit times 63. And then divide it by 1. Oopsie, hang on here. Divided by 169.88. So around 53.2 grams. Sounds about right. and that is of the silver chloride. Okay, I'll type that in again just to double check. Times 143.2 divided by 169. Yep. All right. So again, the problems here, these are things that we did in general chem, so it's nothing new. It is time consuming. I don't know how long this video is while I'm recording it, but I do know that this is a detailed process. It's a very important process. It's definitely something you'll see on the AP exam because this has so many skills involved with chemistry. I mean, it has bouncing of equations, it has bouncing formulas, it has you doing conversions, it has you going through the steps of stoichiometry, it has you test the values for molarity and volume and all that fun stuff. So these are the types of problems that you should anticipate seeing in May. And again, if you are very, very good at this or you're very comfortable with these types of problems, you're in good shape. All right? So again, if you have any questions, please don't hesitate to ask or email. You have my email, and I hope this video has helped.